Okay, guys, we're going to find some critical numbers here. First of all, we've got p minus 1 over p squared plus 4. We're supposed to find the critical numbers, and then at those critical numbers, tell whether the function takes on a maximum value, a minimum value, or perhaps neither one. The first step for doing this is that we're going to find the derivative, because a critical number is where the derivative either equals 0 or fails to exist. In order to see whether those happen, we have to first find the derivative as a function. So f of, oh, well, this is an interesting problem to have. I wrote p. Ha ha ha. Yeah, don't let anybody ever fool you into thinking that I'm smart. So f prime of p is, this is a quotient, f prime g minus g prime f, or if you like, in u and v terminology, because we're already using f, this is u prime v minus v prime u all over v squared. So f prime of p will be the derivative of the top, that's 1, times the bottom, normal style, p squared plus 4, minus the derivative of the bottom, which is 2p, times the normal version of the top, which is p minus 1. And on the bottom, we've got p squared plus 4 squared. Now, it's easy to get intimidated by things like this when there's so many variables floating all over the place. However, keep in mind, what we want here is for this either to not exist or to be equal to 0. The does not exist means that we pay attention to the bottom. The bottom is never equal to 0 because p squared plus 4 can never be 0 because p squared, if p is a real number, can't be negative 4. So the bottom is not going to contribute to this at all. So we're not going to worry about the derivative not existing. I mean, it can happen in general, sure, but not for this specific function. We're just going to worry about when it's equal to 0. A fraction is equal to 0 when the top is equal to 0. So in fact, the bottom, sure, it matters for the values of the derivative, but as far as critical numbers go, we can just pay attention to the top here. So the top, the critical numbers will be when just the top of this equals 0. So I'm going to expand the top, p squared plus 4 minus 2p squared plus 2p. That's a plus because a minus times a minus is a plus. Okay. So if this is going to be equal to 0, then I'd better do some like terms here. So negative 2p squared plus 2p is negative p squared. That's plus 2p and plus 4. And minus signs always ruin my day, so I'm going to times everything by negative 1, p squared minus 2p minus 4 equals 0. Okay, so now I have to go and find the critical numbers here. That this is going to be a little bit inconvenient because I don't think this is going to factor. I tell you what I'll do. I will complete the square. I'll do p squared minus 2p equals 4. So, and then cut the negative 2 in half. That's negative 1. Square it, add it to both sides. That's p squared minus 2p plus 1. That'll be equal to 5. Because over here, I also added 1 on the right-hand side. On the left, this is now p minus 1 squared equals 5. And therefore, p minus 1 will be equal to the positive or negative square root of 5, meaning that p is equal to 1 plus or minus square root of 5. Okay, so the usual thing that we do here is that we would construct a number line at this point. We are going to do that, but we're not going to plug the values on either side of these back into the original, because remember, the bottom is never equal to 0. That means that it will always be, let me see, I shouldn't have put quite so much erasing here. This is p squared plus 4. So specifically, the bottom of that will always be a positive number. That means that it's not going to affect whether the derivative is positive or negative. The derivative will be positive or negative according to whether the top is positive or negative. So I can look at the top and see that it is an inverted parabola. This right here, or well, actually, I'll box something different. This right here is the top. That is an inverted parabola. It goes like this. So I know that when I draw a number line, I've got -1 minus root 5 down here, and -1 plus root 5 up here. Those are my p-values, and then f prime of p is 0 at those values, but it's an inverted parabola. That means that it looks like this. And so it's going to be positive between its zeros. Now I'll use a different color. Positive between its zeros and negative outside of its zeros. So we would expect to see a local minimum value here and the local maximum value here. The reason is that when a function stops decreasing and starts increasing, at that point it has reached a local minimum. And when a function stops increasing and starts decreasing, at that point it has reached a local maximum. All right, let's do another one. Same instructions. So we have to find the derivative first. This time I did get the x correct. Isn't that nice? Let's say that I want to write this using product rule. I could say this is equal to ln x over x squared and then do quotient rule, but I just did quotient rule. Now I want to do product rule. So product rule is u prime v plus v prime u. Derivative of one, they take turns. So this will be -2x to the -3 times ln x, and then plus 1 over x times, nope, not 2, times just normal x to the -2nd. All right, let me collect this. This will be -2 ln x over x to the 3rd. That's what that is. And then plus 1 over x times 1 over x squared is going to give me 1 over x to the 3rd. Notice how these both have an x to the 3rd in the bottom. So this is -2 ln x plus 1 over x cubed. Now you got to pay attention to the fact that a derivative of a function cannot have a domain that's larger than the original domain of the function. So notice that this has a domain that excludes 0 naturally, because you can't do 0 to the -2nd power. You also can't do ln of 0. So it's tempting to say that this derivative right here fails to exist at 0. Well, it's true. It does fail to exist at 0. You can't plug in 0 to that formula, but 0 is already outside the domain in the first place. So we're not going to really worry about it having a critical value there. So let's see. For this to fail to exist, the bottom would need to be 0. But we can't put 0 in anyway. There's another case where it could fail to exist, and that's if we tried to take ln of 0. But the same deal, we can't put in 0 because it's not in the domain of the original function. So just like before, this doesn't always happen, but it happens to have happened these times. Just like before, we can't put in anything for the bottom that will cause this to change. We can't even put in things on either side of 0, because you also can't take the natural log of a negative number. So in fact, the domain very specifically is that x is strictly greater than 0. All right, well, what that means is that yes, we do get to ignore the bottom. And now we're looking for the critical numbers given by -2 ln x plus 1 equals 0. The top of the fraction equals 0. This leads us to -2 ln x equals -1, or ln x equals 1/2. This means x must be equal to e to the 1/2 power, or we would usually write that as square root of e. Okay, it's not totally obvious, the way that the number line is going to work out. So let's get this diagrammed. Square root of e, well, e is like 2.7 something. So if you put, you can't put 0, but if you put 1 in, that's to the left of square root of e, because square root of 2.7 is like, it's more than square root of 2, and square root of 2 is 1.4-ish. So 1 is definitely below square root of e. So we can put the 0 right there. That's where the derivative is 0. We can put as a left-hand test point, put in 1 for x. So f prime of 1, let me do that down here. F prime of 1, that's -2 ln 1 plus 1 over 1 cubed. ln of 1 is 0. So this is 0 plus 1 over 1 cubed. So this is a positive number. Remember, I don't really care what specific number. I just want to know if it's positive or negative. And now for something bigger than that, let me do like e squared, just so that the ln will be easy. So f prime of e squared, -2 ln e squared plus 1 over e squared to the 3rd power. And this will be -2 times, what is ln of e squared? Think about what ln means. It's the inverse of natural exponentiation. So that's going to be 2. That means -2 times 2 plus 1 over e to the 6th. Now that e to the 6th down there is just going to be chilling doing its positive number thing. That's fine. It doesn't really matter for our purposes. What we get up here is -4 plus 1 over e to the 6th. -4 plus 1 is -3 over e to the 6th. So this is equal to a negative number. And what we can see here is that this is a local maximum, because it used to be increasing and has turned into decreasing. I believe I have one more here. Oh yeah, okay, same instructions. G prime of theta is going to be equal to 4 minus, and everybody knows that the derivative of tangent is secant squared, right? If you don't know that, you can verify it using the quotient rule. So 4 minus secant squared theta. We want this to either be 0 or fail to exist. Where does it fail to exist? The derivative of this fails to exist when cosine is equal to 0, because for this is 1 over cosine squared of theta. And cosine squared will, of course, be 0 when cosine is 0. So secant squared will fail to exist when cosine equals 0. Well, cosine equals 0 is already eliminated from the domain of this function because tangent is sine over cosine. So the derivative is only going to fail to exist at the points where this function has vertical asymptotes anyway, and it's not possible for the function to have actual like local max or min values there, but we really shouldn't be listing them anyway because they're not even in the domain. So we're not going to worry about tangent causing the function not to exist. Or rather, we're not going to worry about secant causing the derivative not to exist. So this one is out of the question. We need to see when it's equal to 0, though. 4 minus secant squared equals 0 means that secant squared is going to be 4, or secant without the square, secant theta is equal to either positive or -2. Well, it's more visual, more intuitive to get these in terms of sines and cosines. So this really means that cosine equals positive or negative 1/2. Remember your unit circle? Cosine equals positive or negative 1/2 at these points. This is pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So these are the critical numbers. And we would have this like, let me see, is this going to happen over and over? Like, let's, yeah, it is going to happen over and over, but let's just look at one period to keep things simple. Let's see, we would have pi over 3, then 2 pi over 3, then 4 pi over 3, then 5 pi over 3. Okay, we know that it's 0 at all those points. These are theta values, and these are g prime of theta values. So let's look at what happens in between, or to the left of, rather, pi over 3. And I'm going to look at that specifically as being in this range of angle values. So let me look at, like, pi over 4, for example. That's before then. At pi over 4, we've got 4 minus, where can I write this? It's not f, it's g. G prime of pi over 4. G prime of pi over 4 is going to be 4 minus secant squared of pi over 4, which is 4 minus, now think about it, secant is 1 over cosine. So cosine of pi over 4 is root 2 over 2. Square that, and you get 1/2. But now do the reverse of that, the reciprocal of that. That'll be 4 minus 2. That's equal to 2. So I have that prior to the pi over 3, this is positive. Now look at something in this range between the pi over 3 and 2 pi over 3. The most natural choice is pi over 2 right there. So I'll say g prime of pi over 2 is 4 minus secant squared of pi over 2. Secant squared of pi over 2, that is going to be, oh, this is going to be one of those values that I said we can ignore, because it actually is a point where it doesn't exist. But I suppose that we do have to look on either side of that. So we have more things to test. We have to go there and also there. So let's do something in between pi over 3 and pi over 2. We can take, this is a little squishy, but let's get something in there. In there, you have 4 minus secant squared of an angle between pi over 3 and pi over 2. In this small interval here, cosine is getting to be a smaller magnitude of number. So secant will be getting to be a larger magnitude of number, and it will be positive the whole time. So 4 minus, well, secant squared is always positive. So 4 minus a big number, that's going to be a negative in there. And look on the other side. See, does it happen here as well? In between pi over 2 and 2 pi over 3, you have, again, cosine is going to be small in that interval, and that means that secant is going to be large. 4 minus secant squared is going to be, once more, negative. So far, we do have this classified as a maximum point, because we went from positive to negative there. But as you jump over the does not exist value here, you don't change behavior of the derivative. The function is decreasing before the asymptote and after the asymptote. Let's go from 2 pi over 3 to 4 pi over 3. So now we're going to be testing in here. Okay, the most natural thing to check there is pi. So g prime of pi is 4 minus secant squared of pi. Secant of pi is -1 because that's the cosine of -1. 1 over -1 is -1. But 4 minus -1 squared is 4 minus 1, which is 3. So the derivative is positive on that interval. What that means is that this is a minimum. Now, we're going to run into the same problem here at 3 pi over 2 that we ran into between the pi over 3 and 2 pi over 3. There's going to be what's called in math sometimes a singularity, a vertical asymptote right there. So we'll have to look at these separately. We'll look at this little segment down here, and then separately we'll look at this little segment down here. Okay, let's look at this. In that interval, secant will be large because cosine is small. 4 minus a big number means that we're going to have negative values in here. Then at 3 pi over 2, the derivative doesn't exist. And then for the same reason as before, over here, you've got 4 minus a big number. That likewise is going to be a negative value. So once again, jumping over the asymptote, you don't switch from negative to positive. The function is decreasing on both sides of the asymptote. Okay, one more. Now we go in this interval right here. For that, let's take, we can even take 0 for that because we didn't find that it switches behavior there, so why not? G prime of actually 0. 4 minus secant squared of 0. And that will be, let's see, 4 minus 1 squared, which is 3. So this is positive. So the last couple of classifications we've got here are that 4 pi over 3 is a maximum, and 5 pi over 3 is a minimum. Thank you so much for sticking with me. That was a long set of problems.